This demo focuses on the use case 1 scenario to showcase the advantages of using the VOStack in complex robotic software implementations in emergency and disaster scenarios.
Here are our robots and the wireless sensor networks.
During the demo day at the Luka Koper Port, our robots were deployed to simulate an emergency scenario involving a fallen container, showcasing how autonomous systems can assist in such critical situations. A phone call was placed to alert the firefighting and security teams to respond to the fallen container emergency at the port. The security team quickly arrived to secure the area, clearing the way for our robotic team to step in and begin the mission. The first mission involves drone-based mapping. On the Foxglove dashboard, the top left displays a 2D map of the area, while the bottom left shows the 3D reconstruction along with the drone's flight path. The top right features live video streaming from the drone, and the bottom right presents the drone's GPS position overlaid on the map. The second mission focuses on mapping and detection using the Summit XL. We initiate the task by triggering ROS processes on the device, which launches the 2D mapping, front camera, and the arm camera detection. Once running, the Foxglove dashboard visualizes the active ROS topics. These include the real-time 2D map, live camera streams, LiDAR data, a virtual representation of the robot in motion, and annotated images highlighting the detected objects in the environment. One of the primary objectives in this mission is person and liquid detection, critical for assessing emergency situations. We use Tiny YOLO v4 for real-time person detection and a liquid detection model to identify potential spills. Detected elements are marked directly on the map. Red indicates liquid, yellow marks a laying person, and green represents a standing person. Another key task is mapping, providing crucial spatial awareness for both operators and autonomous systems. 2D maps are generated in real time using LiDAR data, offering a floor plan-like view for navigation and planning. Simultaneously, the arm camera builds a 3D reconstruction of the environment.
To manage the wireless sensor network, we developed an intuitive web application called WSN Planner and Controller. This app allows us to create pre-configured missions with default settings. For the demonstration at Luka Koper Port, the default setting starts with 2 Pi senses and 1 Raspberry gateway. We can choose which sensors to activate on each node. For this demo, we didn't need the accelerometer. A summary screen lets us name the mission before launching it. Once configured, we place the selected nodes on the robot and wait for it to be ready. The WSN app then waits for the map sent from the robot to the VO, the CVO, and the WSN API. Once received, the map is displayed in the web app. The right side shows live map data from the robot. The left side shows the list of nodes selected and installed on the robot.
First responders can now select where to place the sensor nodes on the map. In this demo, both nodes are placed around containers in the risky area. These coordinates are saved and sent to the CVO using the VOStack. The robot moves to the specified area to position the nodes. The first sensor data is sent to the Raspberry Pi gateway, then to VO3. The WSN API can retrieve this data that can be displayed in the web app.
We can click the button at the top right to view an ongoing mission. On the graph, we noticed that the PiSense node ending in 9C is not working anymore. We can select a backup node ending in A4, configure it and mount it on the Summit XL. Here we choose to only activate the temperature sensor. Up to 2 nodes can be deployed at a time. Once the coordinates are sent to the robot, it moves again to the designated location and the same process is repeated to receive the sensor data.
To conclude, thanks to the use of modern web frameworks, we implemented an efficient WSN planner and controller. The third task in this use case involves sensor deployment, which is where the WSN planner and controller application comes into play.
The final task is liquid sampling. The coordinates for sampling are obtained from the liquid detection and localization process. Sampling is initiated through the Flask GUI, which sends a command to the robot to start the mission. The robot autonomously navigates to the target location and uses a cotton swab attached to its gripper to collect the liquid sample, placing it back into the pallet afterward.